Hi, so my name's Eli Jones.
And my name is Hunter Reese.
And kind of what our project is going to be about is we're trying to develop a novel transgenic bacteria that can detoxify arsenic in groundwater, potentially saving millions of lives. So I guess we should kind of start off with what the problem is. So arsenic will leach into groundwater because of mineral deposits which run down from mountainous regions in the low-lying groundwater and source water areas. So a lot of this will happen like in the Gangetic Plains region, and it's extremely hard to stop because the thing here is you can't really stop natural deposits of arsenic from entering the groundwater. Now you can stop anthropogenic or human-made sources from getting into the water, but we can't really do that with natural sources like this arsenic that's entering the water.
So what's happening when arsenic is entering the water? It's entering people's source of drinking water. Now if people are drinking water with higher concentrations, then there are multiple health effects that come with that. Like, for example, a long-term long-term health effect of having arsenic in your water can be various types of cancer, and it can also cause blindness. Now, and of course, the most obvious one is death. And in regions like Bangladesh and India, we're seeing large amounts of people dying or becoming sick due to these arsenic concentrations. And it's really just been detrimental to millions and millions of people over the years.
Yeah, so kind of what kind of the problem here is that we have multiple people developing solutions. Of course, ever since the 1800s, people have been exposed to this arsenic because of growing populations, of course. And of course, we've also seen the development of many systems, like the ion exchange system. This is one system that actually replaces arsenic with phosphate. Now, this system is used a lot in the United States because it can potentially detoxify the arsenic concentration by a really great deal. But the problem with this system is it costs multiple hundreds of thousands of dollars. It takes maintenance, it takes electricity, and also it does not completely detoxify the arsenic. It still leaves all the arsenic behind because it cannot detoxify completely. So kind of what scientists have been starting to develop is they've been saying, okay, well, we're not going to be able to actually use a physical device. Some of these countries are just so poor, we cannot have a physical device up there detoxifying thousands of gallons and liters of this water. So we have to figure out some new method. And of course, this new method is going to be bioremediation, using bacteria and metabolic mechanisms in this bacteria to detoxify the arsenic. Now, I'll kind of let Hunter get into the bacteria we started studying.
So the two main forms of arsenic really quick, they're arsenite and arsenate, which Eli talked about. These ion exchange, arsenite right here. Well, the problem is as he's mentioned, this ion exchange system is leaving behind the rest of the arsenite. But what we found is that there's certain bacteria that can oxidize that arsenite and turn it into arsenate. Now that provides a 60 times decrease in toxicity. One bacteria that is very noteworthy is Rhizobium strain NT26. This bacteria is one of the only bacteria that can oxidize arsenite autotrophically and fast and all this, but the main problem is NT26 can survive in only very few environments, and it's very sensitive and it's found in only specific locations. So our main goal of this experiment is to take those genes that are responsible for arsenite oxidation and use basics of gene cloning to take those genes and put it into another bacteria that's more robust, that can survive in all kinds of environments, and is also safe for people and their drinking water. So the main hope is that we could take these new bacteria that have the arsenite oxidase genes and put it in water so that people could have safe drinking water without toxic arsenic.
So I'll kind of get into the materials and methods section of this. But of course, I'm going to first show you, this is a micrograph of Rhizobium strain NT26. And what we actually had to do is we had to isolate this strain from, we had to have a lab send this strain of bacteria to us because it's extremely rare. And once we had this bacteria, we were able to actually extract its genes using a TES and lysis buffer, which lysed the cell and of course gave us all of our DNA. Now this is where we get into the major part of the experiment. We have all of its DNA. Now we have to actually develop this gene cluster, figure out what gene cluster is responsible for arsenite oxidation. So of course, we were able to use NCBI and multiple published websites that have studied the specific proteins responsible for this and determined all the proteins that are required for arsenite oxidation in gram-negative bacteria. From there, we designed specific primers, which are little segments of DNA that bind to that chromosomal DNA that we just extracted. And with those primers, we were able to run polymerase chain reaction, which multiplies those segments of DNA multiple millions of times. So once we have those segments of DNA extracted, we are able to use it, restriction digestion to basically clip the ends of this DNA and insert it into something called an expression vector, the PBAT30 expression vector, which allows you to make multiple copies of this gene within bacteria. Now, we also digested this expression vector, which allows it kind of to fit in almost like a puzzle piece, this gene cluster in the expression vector. And then we ligated it, which is like stapling it shut, kind of like you would staple together two puzzle pieces. You wouldn't do that. But once...
I've never stapled two puzzle pieces.
Okay. Anyway, what you were saying?
What's your time?
Once you have that recombinant vector, what we actually did is we would be able to make our E. coli C600 electrocompetent. And what this allows it to do is it takes up this vector and is potentially going to be able to express this gene. Now, of course, before we get it to express the gene, we need to figure out what bacteria has the recombinant vector, because that is a bacteria that could potentially save lives. And we need to figure out what the bacteria is. So we'll put that on an ampicillin selective plate, because the this PBAT30 expression vector produces a certain protein that allows it to grow on ampicillin, unlike normal bacteria. So once we have that bacteria isolated by growing it on an ampicillin plate, we're able to actually express that gene using arabinose. And once we express that gene, we're going to be able to start getting into the tests to determine whether or not our transgenic bacteria, which we were able to successfully develop, as you can see right here, we were able to extract that gene, and we were able to actually see growth of the bacteria once we put it on the ampicillin plate. So I'll let you kind of talk about the results.
So yes, after we saw this little colony growing on the plate, we knew that we had a transgenic bacteria, and we also knew that it contained the genes responsible for arsenite oxidation. So after this, not only did we know it had the genes responsible for arsenite oxidation, but we had to know if it could oxidize arsenite and then compare it to NT26, which is the fastest arsenite oxidizer. So first what we did is we developed our own test. Our first test was just a confirmatory test to see, did it oxidize arsenite at all? So what we did is we added silver nitrate to a 32-hour growth of this new transgenic bacteria, and we found with this diagram, based on the silver nitrate test, that our transgenic bacteria did oxidize arsenite, and now it converted that to arsenate. So once we know this, we needed to know, well, not only did it oxidize arsenite, but how well did it compare to NT26, and can we actually implement this in the waters? So what we did is we developed a new quantitative method to show how much it actually oxidized arsenite.
And so this new quantitative method is just based on the silver nitrate test. What it does is we take samples of our bacteria oxidizing arsenite over time, put that in a 96-well spot plate, add a small volume of silver nitrate, and once we've done that, we'd be able to take a photograph of that bacteria using consistent background, and then analyze those color values on Adobe Photoshop. Now, the reason why we're analyzing color values is, of course, because arsenate, when it forms a complex with silver, forms a red precipitate. Arsenite forms yellow precipitate. So if we can figure out what that ratio of red to yellow is percentage-wise, we'd be able to pretty much figure out the percentage of arsenite oxidation. So what we did is we actually used a red to yellow hue chart to develop a mathematical equation that can relate these color values to the actual percent arsenite oxidation. This is that equation right here. And using that mathematical equation, we were able to figure out the arsenite oxidation over time. And we found the line of best fit, which showed that it oxidized approximately 25% of the arsenite, which has incredible implications for just being over a 32-hour period.
So once we know how well it oxidized arsenite over this 32-hour period, this meant very good news for us. So as you know, you can never take NT26 and put it in water and expect it to solve the problem of arsenic contamination, because it would just simply die in the water. But now what we found is that we have a bacteria that we made that is resilient to the water and that is safe to drink, that we can actually add to source water itself, and we can see that it will, in fact, oxidize arsenite. And you may say, well, it's only 25%. But this is very significant because over a longer amount of time, when you add it to the water, it's going to replicate even faster than NT26, in fact, and it could oxidize all of the arsenite in the water and make it 60 times safer to drink.
Yes. So do you have any questions about our project?
Excellent. 18 seconds remaining.
Oh, total?
No, of your 10 minutes.
Oh, okay.
So that's good. So then you've got 5 minutes left. I have a list of questions that we'll talk about when we get there, but for now, let's still work on the presentation. You are talking so fast. Like, you're gonna have to take a deep breath, breathe through. Much better overall. On average.
I realized it after you started it. I thought I had already done that, but I didn't.
And each one of these